One sample t-test is used when we have information about the sample, in most cases the mean and standard deviation, and we want to ascertain whether the sample comes from a particular population. The formula we use in getting the calculated value when we are testing the null hypothesis is that t is equal to what we have here, whereby this value here is the sample mean, this is the hypothesized mean, this is the sample standard deviation, and this is the sample size. So we have an example there. A machine is designed to pack 500 milliliters of liquid. A spot check revealed the following content in a sample of 12 bottles that it packed this morning. Then at alpha of 0.05, deduce whether the machine's performance lives up to its expectation. Solution. We first of all come up with the hypothesis. The null hypothesis says or states that the mean is equal to 500. This is the mean of the population. So we say the mean is equal to the 500 that pertains to the mean of the population. The alternative hypothesis comes from the question. We have to deduce whether the machine lives to its expectation, if its performance lives up to its expectation. So here the answer is actually yes or no. And if we look at it, then it does not give a direction whether we are interested in the machine performing better or worse. So that's why we are using not equal sign, and that means these are two-tailed test. Now we need to calculate the mean for the sample and the standard deviation. That's why we have these columns here, this table. Now the X column represents the content for the 12 bottles for the sample. So we listed them column wise, and then when we have listed all of them, we need the total, the sum of this column X, and if you calculate well, you get 6026, that is 6026, and that will be used to calculate the mean. So we shall say mean of that sample is equal to summation X, which is 6026, over the sample size, which is 12. If you divide that, you are likely to get 502.1667. Now that sample mean is used to calculate this column for deviation, and that this column simply means you take the values in the X column minus the mean we have calculated. That will give you the deviation of every value from the mean. So the first one will be 497 minus 502.17. This 502.17 is the mean we have just calculated here, rounded to 2 decimal places. So the first one will be calculated as I've said, and that gives you negative 5.17. The second one will be calculated by taking 498 minus 502.17. If you do that, you get negative 4.17, and that's how you calculate the rest up to the last one, which will be found by taking 503 minus 502.17, and that gives you 0.83. Now this next column here is d squared, and it means you take the values you have found here, square them, and you get the values to write here. So the first one will be found by taking negative 5.17, you square that, and that will give you 26.73. This second one will be found by taking negative 4.17, square it, you get 17.39, and you work out the rest like that up to the last one, which is 0.83 squared, giving you 0.69. Now we also need this sum. We also need this summation, the sum. So we shall say summation d squared is equal to, if you add all this, you're likely to get 611.67, and that is summation d squared. Now with that, we can be able to calculate variance and standard deviation. So standard deviation will be calculated as S is equal to summation d squared over n minus 1. That one will give you variance, but because we want standard deviation, we need to get the square root of that. So we shall get the square root of variance, meaning the square root of summation d squared over n minus 1. And if you do that, it means our summation d squared here is this one, 611.67. That's what will be on the numerator side. On the denominator side, we shall have 12 minus 1. So here we shall have 12 minus 1, and that gives us 11. So that will simplify to the square root of 611.67 over 11. And that one, if you simplify, you get 7.46. This is the standard deviation. Remember, this is the variance, and we get standard deviation from the variance by getting the square root. So we now have the sample mean and the sample standard deviation. So we shall now come up here, pick our formula for calculating the t-value, and say t-calc is equal to what we have up there, and that is equal to, on the numerator side, we shall have x bar, this one being this value we calculated, 502.17. We have rounded it off to 2 decimal places, minus this one is the population mean, which we have been given here, over S is the standard deviation, which we have just calculated here and found to be 7.46, over root n. Root n means the square root of the sample size. The sample is 12. Now from our calculator, we can get the square root of 12. So we shall have it reduced to, when you subtract this, you get 2.17 over 7.46 over square root what? Good. From our calculator, you get 3.46. Simplify this, 7.46 divided by 3.46. So that will be 2.17 over 2.16. 2.16 is from the fact that we have divided 7.46 by 3.46. If you simplify this, you will get 1.00 when you round it correct to decimal places. This is our t calculated. So we shall say our t calc is 1.00. The next thing is to calculate, to get the t value from the table, what we call the critical value. So we need degrees of freedom to achieve that. The degrees of freedom are given by sample size less 1. Our sample size is 12. So 12 minus 1 gives us 11. Excuse me. And that is the value we shall use in getting the t critical. Then we have our table here. We have our degrees of freedom, they are 11. So we shall look for 11 here. Then up here, remember from the alternative hypothesis, we agreed that the presence of this not equal sign means it's a two-tailed test. So we shall look for 0.05 and a two-tailed. Two-tailed is the one which is written on top here. Remember the captions here are two. We have the first one here for two-tailed, and then there is for one-tailed. We shall look for two-tailed where 5 is. 5 is here. So you move down and you move across 11, then you will get 2.201. So that means the t critical is 2.201. What is written here is simply to tell us that this is a two-tailed test, and this is the degrees of freedom. Indeed, the degrees of freedom we have used are 11, and when we take alpha over 2, it's like we are converting the two-tailed to one test, which is actually like the same as this 2.5. So it does not make any difference whether you just read the two-tailed test direct up here or you use the second one after we have divided by 2. So now to make the decision, compare the critical value, which is 2.201 versus the calculated value, which is 1.00. So you realize clearly the calculated value is less than the table value, which we call the critical value. And therefore, we say since the t calculated is less than the t critical, that means we shall fail to reject the null hypothesis and conclude that there is no difference between the sample mean and the population mean, meaning that the machine's performance lives up to its expectation. In other words, there is no major difference or significant difference between the sample mean and the population mean. Thank you.